Okay, thanks very much. So about 18 months ago, I saw Sotabeams release their Whisper Lite, which was a hugely successful product, a standalone Whisper beacon, and was used by a large number of people, contributed hugely to the Whisper network, which helps us investigate propagation, spot openings, etc. And this was interesting, but it only offered a transmit feature, and there was a couple of other things that I wanted as well, so I decided to have a go at it myself. The thing with electronic design is round one tends to look like this. And one of the big things with our hobby is there's so much interest in all sorts of areas that if you think something is really cool and worth your time building, someone else probably does too. And one of these is okay for one, but if you want 20 of these, you're going to have some very long evenings. So one of the big things I always do when I'm first trying to design something is I actually bring it up at my local club, the Camhams. Some of the best design review meetings I've had have been in a car on the way to Brecon Beacons to on a SOTA trip, and in the pub. And this is one of the huge values of clubs. There's so many people with so many different ideas, so many perspectives, that you come in with one idea, you know, half an hour chat, and it's been improved massively. So that's generally how I start my ideas, find the features that people are interested in. But when you've come up with this design and you've got your magic gizmo, obviously you can't ship a load of these. There's so much potential for error. If you want to sit there building these all day, that's fine, but I don't have time for this. So what I was looking at was coming up with a solution that could be easily repeated for a lot of people, was sort of a robust, you know, I don't fancy putting that through Heathrow baggage handling, it probably won't come out intact, but could also be upgraded in the future because no design is perfect. You will find things that you want to either add or fix. And yeah. So we should always design as if what we're building isn't a one-off, because you don't have to do many runs for it to become, for the mindset of production testing to actually become important. So, covering HF Whisper transceiver, I'm sure many of you have been exposed to Whisper. It's an automated tool generally used to monitor propagation. Spots are then uploaded to the Whisper network, and you sort of get pretty graphs. This was 30 meters on Thursday evening. I'm going to go with, it was open to the States at that time, based on the activity. However, Whisper is actually electronically a fairly simple mode. It uses frequency shift keying, which means it sends a single tone, and it just varies the frequency of that tone to encode your message. So from a design perspective, it's actually not that complicated. There's a lot of clever stuff gone into the encoding to generate those tones, but actually from an RF standpoint, it's not that complex. So if all we have to do is generate this tone, there's a huge number of integrated circuits that are available on the market that will generate a wide range of frequencies. Looking at RS this morning, Silicon Labs have one, the SI5351, which is used in all sorts of things. It is used in Sotabeam's product and also Hans Sommer's range of QCX transceivers, some of the CW ones, I believe. It costs £1, and with a bit of software programming, will generate pretty much any frequency you like from 8 kilohertz up to 133 megahertz. Probably when it's generating the frequency you ask it for, it's generating a load of others as well, but we have filters for this. So there's a huge range of these synthesizer chips that are available at very low cost, that with a small amount of software, we can generate the tones. So we've got the tones, so next step, stick it into an antenna. It was about us. And that is my first prototype of the transmitter. This thing at the bottom here is effectively an Arduino. That is a Adafruit breakout board for this 5351. Going into a low-pass filter straight into my antenna. Output power, about 10 milliwatts. It got me across the Atlantic. It was received in East Coast states. So, you know, in total in that picture, you know, if you replace that with an Arduino board from, you know, you're looking under a tenner. So a whisper transmitter is not actually that complicated. We can just go synthesizer, some sort of power amplifier if we want it, low pass filter, jobs are good. So receiver, it's also actually not that complicated. There are loads of SDR dongles available as one option. You could just plug it into something like a Raspberry Pi, your PC at home, run the Whisper software, and we're done, right? So this talk, I'm not going to discuss receiver design. There's not the time. But actually, from a fundamental standpoint, it's not that difficult. You can just mix it down to audio levels, shove it into a PC, and you're done. So what I'm actually going to talk about is some of the design aspects that take this from a Pi with a couple of boards and some wires into actually something that is repeatable, robust, and standalone. So the first thing you should do whenever doing a project, and this is done wrong so many times, is you should start with the enclosure. So many times you build this wonderful gizmo, you have the circuit boards on your desk, and then you go, right, and now what? You've got LCDs hanging off ribbon cables, nothing fits nicely. So all these good product design really should start with thinking how you're going to enclose this, because this can put huge constraints on your design or huge opportunities depending how it's what you take into consideration. But this is important. Your case needs to protect your things, needs to keep it robust, RF shielding, and also it just gives that professional look. A couple of pieces of Veriboard type sort of screwed to a piece of MDF isn't going to go very far. So this was a project I did a while back. This is a USB to RS232 and Winky interface for a K3, but that box that it's in is a serial port connector, so is about 2 inches tall. And obviously it's made a huge effect on your design choices, how you do it. Those components used they're manageable, but they're quite fiddly. They're 0402 for anyone interested. But if I considered this without thinking out how I was going to box it, I would have never come up with a design like this. One of my favorite methods of enclosing things is these. So these are 2-part extruded aluminium cases. They're available about £3 on Amazon or eBay. You do have to, the shipping does take several months in some cases because most of the sellers are sort of Chinese if you're paying that lower price, but it's one of those you get what you pay for in terms of the shipping speed. But these are excellent cases. They're very easy to construct with. I don't know if you can see on this picture, but they actually have slots built into them for sliding PCBs into. So if you've taken that into consideration and you build your PCB to the dimensions specified by by the box, then you have a really easy time putting it in enclosure. The other really nice thing about these is they have flat front panels, which makes them really easy to use, a piece of aluminium or something. But the thing is, with front panels, if you just use a piece of aluminium and you have 30 people then go, yes, I'd like one of those, you then have to sit there drilling, labeling 30 panels, which gets very tedious. A job which takes you 2 hours, which might be fine on a Sunday afternoon for yourself. If you have 20 orders, you're basically coming up to a full working week's worth of hours. And that gets very tedious very quickly. Which brings us on to the next point of circuit boards are amazing. There seems to be a lot of resistance to using circuit boards. Veriboard is a perfectly viable construction, but it just doesn't scale well. If you build 2, it takes twice as long as it does to build 1. And all the sort of potential for errors and faults that may have. And they're really not that expensive. These are from the suppliers I use. 10 boards for $2. On some small panels, this can turn into several hundred units for $2 of circuit board. So even if you try it, they're worth doing even from a prototyping stage, just because it means your connections are solid. You're not going to have, if you can solder to the circuit board, your connections you shouldn't have intermittent connections. You can, use proper transmission lines for everything, and they just open so much scope up. And, the hobbyist market has really brought the price down lately, so it is well worth taking the time, because any time invested in a circuit board will repay itself as soon as you have to make more than one unit. And the other thing it gives us is it gives us access to parts which are almost impossible on any other form of prototyping. The semiconductor industry is doing amazing things at the moment. You know, we're getting chips that can sample at hundreds of megahertz, can generate frequencies on a wide range, have an outstanding performance. But the thing is, if we stick purely with strip boards and sort of hand wire constructions, we're going to get left behind or not be able to take advantage of all the improvements that's happening in development. Very few RF chips nowadays will come in any package that is, you know, reasonably feasible in more than one-off quantities, soldering by hand. However, PCBs are often seen as, okay, it's a way I connect a load of components together. But actually, that's not just all they're good for. If we think about it, a PCB is custom milled, custom sized, custom drilled, and they do silkscreen on both sides. So actually, going back to our aluminium box panel, it's how actually I make a lot of front panels for things. So that there is a circuit board. It has no copper traces on this side. But if you tried to do a similar thing in metal, you know, getting a quote for a manufacturer to produce something similar would be hugely expensive. And you can specify very complex shapes. So the antenna connection there takes a BNC through it. So that's not a particularly big hole, and they're capable of milling that out, you know, for $2 for 10 copies. And when you put the parts in, you know, it's professional for 20 cents. I mean, what more can you ask for? You know, any look like that when they come from the factory like that, and all you do is put them on, you know, anything else struggles to compete. You can also use them for front panels. So this one here is the front panel for the same unit. This is my WSPR transceiver. Again, very little functionality, but getting that milled in metal would be complicated, getting that milled with all the labeling. One interesting thing to point out here is that these boards, the actual material they're made of is actually grey. If we look at this edge here, you can see that a circuit board is sort of opaque-ish, slightly white, which looks a bit rubbish. But if we look at the top here, we can see that they're nice and black. Where you do that is a permanent marker. Just sit there, permanent marker along the top, looks nice and black. I've got some examples of this at the front if anyone wants to come and have a look afterwards. So the PCBs are amazing, but when we buy a PCB, you buy it by area and the tolerances to which you want the manufacturer to make it. So when you've got that area anyway, because it needs to fit in your box, you might as well make the most of it. And this is where small efforts in design can really reap the rewards later. So this is an example. This is the power connector. But what I actually have here is two power connectors on top of each other. I own an aircraft rig, so most of my station is run off power poles. So these two pins here, and sort of this large outer box, is a power pole connector. But also I'm aware that not everyone uses that. It's one of those things you tend to adopt as full SHAP policy or not. I'm aware some people haven't. So this in the middle is a 2.1 millimeter barrel jack. So that's cost me nothing to add, but it means if you give it to someone who doesn't use power poles, it's just as functional for them. And then all you do is you solder in whichever connector you want. So actually putting in that flexibility to allow for multiple connectors to be used, if you've got the area anyway, you know, it's 5 seconds extra on the circuit board because most things have libraries for all the common connectors. If you just 5 seconds of thinking there means that you supply one board and it can work for more than one person. Now, in an ideal world, we would build our circuit board, we would power it on, it would work perfectly, and we go and that's a good day. However, it doesn't work like that. Things are not going to work, which means you're going to have to debug it. And this is another example of where a bit of effort at the start can save you a lot of headache later. Now, I've certainly done this, and I suspect many people who've built things have as well. You have the board in front of you trying to see exactly where to put that scope probe. You have two pieces of paper telling you, one of which tells you the signal you want is on pin 9 of U2, and another one telling you where on earth U2 is because it's not marked on the board. However, once again, we've paid for the area. Label all our connectors. If you label the pins on your connector, you save yourself so much time later. And yes, it does have a genuine bodge wire at the bottom. This is still slightly in development, so I added that for authenticity. But it means that when I come to that, or someone else builds one, and it's not working and not sure why, if you tell them to look at the audio line, you know, it's on the board there for you. And also people lose documentation, you forget where it is, documentation can get out of date, you know, if someone's using an older version of the board. But if it's written on the board, if you've labeled it right, it's fine. This doesn't just apply to circuit boards, even strip board construction. Just, if you literally permanent label, most of my sort of, even if I'm working on variable, I will often scribble all over the board, sort of a couple of kitchen stickers or something, and I write what a lot of the pins are. The other trick, which I'm actually giving credit to my dad, who sat in the front row for, is a white heat shrink. If you write on it with permanent marker around your cable, and then shrink it down, you have a permanent label. It's not going to fall off like a bit of tape folded around it like I used to do. And that's a very nice way to indicate what your cables are for, what they're doing. And it means that when you even get a hugely complicated board, so this is actually my 4th year project at uni, you can actually write notes to yourself. So not just necessarily what the pinouts are, but useful things like here, I've written an instruction that if I short these pads, it pulls the line low, with the lines being labeled there. If we have input-output connectors, all my lines labeled again, and the signaling voltage is surprisingly useful. But also, I don't know if you can read that, this took a flat flex cable on the other side. It tells me which way around to plug the cable in. And just, you write these notes to yourself, because if you write it on a post-it note or write it down on a piece of paper, you might miss it. Whereas that, there is no way to take that away from the connector. The connector itself is actually on the other side of the board, but it means that if you keep your information next to where it matters, you save yourself so much time going back and forth, and transplanting has, you know, possibilities for error. And if you're doing things like connecting power supplies, you know, you don't want to accidentally plug it into a 12-volt rail. You will have a really, really bad day. And this is the other thing that's, when I built this project, this is the same one that goes in the serial port connector. Someone asked me, why have you put an LED on it? It's going in a box. And the answer is, it only goes in a box while it's working. You know, a single LED can give you so much information. So in this one, there's 2 serial ports. The LED blinks green if there's activity on one serial port, blinks red if there's activity on the other. But that means just by looking at my board, I can see if there's activity, and you already start to narrow down the area of the problem without having to take measurements. The first sign that something's going wrong in your circuit should never be smoke coming out of it. And even though it may be overkill to cover your board in LEDs, I generally put one on every single power rail, because that means you plug it in, all your LEDs come on for your different power rails, you know it's working, or at least you know your voltage regulators are on. It's not a problem with the power supply, it's not the problem with power getting it into the board. They take very little current, so don't actually affect that much. I've even seen some designs put the LED straight on a data line to indicate activity. I mean, might affect it slightly, but at low baud rates isn't an issue. If you're space constrained, like you only have a front panel, if you use a bi or even a tricolor LED, you can get so much more information out of this. You know, red, green tells you, that's so much more information than, is it the one where it blinks 3 times and waits, or blinks 4 times then waits, and you end up looking this up anyway. And often if you're putting software in the thing, if you write just a self-test routine at the start that just sort of prods every bit of hardware it should be talking to, and then turns the LED green, it means you can turn it on, the LED goes green, we know everything's connected and working. That is so much quicker than manually going around probing everything, making sure it works. Now, I'm slightly paranoid at this as a result of a picture that's on the next slide, but even if you don't intend that a line be tested in production or use in debugging, they're rarely a bad thing to add. So in this line, My WSPR transceiver has a GPS receiver, which is the sort of part on the left. But I put a pad in its data lines. I will never want to probe that while it's working. But the alternative is you do this, which is never a good idea. You know, the segment of board you can see there is probably under an inch across. That was about half an hour of squinting under a microscope. Wasn't that fun? The other thing I would recommend is never leave a pin. If you have spare pins, bring them out to something useful. Here, it didn't work and I had to debug it. I didn't have any spare lines to look at debug signals, so I ended up doing this. Whereas actually, the main processor, which is just off the screen to the right, had about 20 unused pins that I could have used to tell me what was going on inside. So if you have spare pins and you have the space, if you bring them out to just something that's big enough to easily solder onto, that will save you so much trouble. It also gives you a huge amount of potential for when you decide, oh, I want it to do this extra cool thing, but I need one spare pin to do it. If it's soldering wires onto these processors with, you know, 1/2 mil pin pitch, that is not a fun day. If it's solder a wire to the, you know, 0.1 inch header on the side, that's a much more manageable task. This is something that is not always necessary, but sometimes very useful. If you're actually building the PCBs for other people, you really need to test them before you just give them and go, oh, I can solder perfectly. Of course it works. It doesn't work like that. And one of the things that is really worth thinking about is building test jigs. So what these are generally based on is they're called pogo pins. They're a sort of brass rod with a spring-loaded contact in the end, so you sort of push it down onto your board, and if you push it down such that most of the springs have gone back a bit, you know it's making a good connection. And the great thing is, when you order PCBs, you tend to have spare copies, because if you're getting them 10 copies at a time, you tend not to build up all 10. These PCBs conveniently have holes drilled in exactly the location you wanted. So if you've put your test points in for every line you want to test, you just stick a pogo pin in that, one test jig done. So that one there, that has 2 modes for the switch. Each one, it's flick the switch, LED goes green if it works. So that is testing 3 communications networks and that the win keyer in it works, so checks dot, checks dash, and checks that it's actually keying your rig in about a second, and just lights up the LED green when you're done. Yes, it took me a couple of hours to make, but I tested 15 boards with this in about 10 minutes. So, you know, if you had to sit there with a scope, check all the data lines were working, it just becomes worth it in your time. But yeah, old PCBs make excellent test rigs, and they're well worth thinking about. But again, that comes back to you need to be able to physically get to the pins to test it. So this is the result as it stands at the moment. This is my HF WSPR transceiver. I'll give you a quick rundown of the parts in it. So that here is a PIC processor, doing a very similar job to an Arduino. Power supply circuitry here. Low pass filters here. Receiver chain, power amplifier down that side, and receiver there. So it's quite compact. But we can fit 2 boards in this, which is actually a huge amount of area. These boards only really have components on one side, but if I'd wanted, I could have put components on both sides of those boards, which is an absolute huge amount of working area, given that that is, well, that is the dimension of the box we're talking about. So, you know, a full HF transceiver in that, which arguably could do CW or most of the data modes as well, is pretty good going. And that's just because this flexibility gives us a huge amount of area to work with. Oops, sorry, I'll get that out of the way. But also, I've spent very little time, if I give this to someone, I've spent very little time doing anything. The boxes I buy from eBay, front and rear panel are just circuit boards that come with the regular ones. So in terms of giving everyone all the bits they need to assemble if they solder it themselves, to assemble something into a proper case that looks professional, I've had to do 0 messing around if they're prepared to solder it themselves and buy the parts. And it means that, I don't know, I find it gives you that nice fuzzy feeling when you finish building your thing and it is done, it's not finished, and you there go, right, how do I make it actually, you know, look good and work with my shack? So So yes, I haven't talked about the actual design, but I hope those are a couple of little pointers that to bear in mind in your design. I have been mainly talking about circuit boards, but these techniques can apply. It's amazing how much just 2 minutes with a permanent marker can save you in the long term. So to summarize, anything that's designed to be a final product, you should always think, well, what happens if I have to make 10, 20, 30? Because it's amazing how quickly the time builds up. Enclosures are really important and should actually be one of the driving factors in your design. You should have a clear objective of where you're going and not worry about that later. PCBs are amazing, but they're not just for making electrical traces to something. One of the things I actually missed was when you do the PCB end panels, because you can put copper in them, you can fully shield your case. So if you include copper on the actual panels you're using, you then get a fully shielded case as well. And make life easy for yourself later. Because it may seem tempting while you're spinning up the board, it's 11 o'clock at night, you want to ship it before it's the weekend, so they're working on it. But just that 10 minutes, putting the labels on, making sure that it's easy to test if it doesn't work, will save yourself a huge amount of time later. And you really will thank yourself for it. Okay, thank you very much.
We've still got time for some question and answers. I'm sure there are people with lots to Have you got a link to where you get your enclosures and your PCBs made?
So that was, do I have a link to where I get my enclosures and PCBs? Sorry, they wanted me to repeat it for the streaming viewers. Enclosures, eBay is amazing. I almost type in aluminium extruded enclosure. The search function's a bit weird. They tend to come in very standard sizes. But if you just type in the general term and scroll down a bit, you tend to get most of them. They're available in crazy things from sort of like an inch cubed, sort of all the way up to, sort of 19-inch racks if you want. You can buy on eBay. PCBs, huge number of suppliers available.
Chinese?
Yes, generally. But they've got to the point that turnaround is normally a week, as in a week from submitting order to I have it. If you want exact emails, I can discuss that afterwards. Anyone else?
Do you do any sort of simulation of the circuits before committing to the PCB, or do you generally get involved?
I tend not to simulate, because a lot of what I tend to work on is often has a microcontroller on it. But a lot of the chips, if you go to the manufacturer's website, scroll down in the datasheet, there's normally a reference design. And actually, that's a really good standpoint to work from. So if I'm putting it straight onto a circuit board, I tend to actually go with the reference design for a lot of things. It tells you how to connect the power rails to what. And if you've got that and all you're worrying about is, playing with the data lines in and getting the signal out, you're a huge step there. Other thing is breakout boards are amazing. Companies like Adafruit do very nice breakout boards. There's a picture that I've been told that should never see the light of day of when I took a Stanley knife to a Adafruit board because I wanted to see how a chip behaved, but it didn't just quite have the data lines in the right setting. So I scraped most of the solder resist off and bodged it and then drowned it in hot glue. Yes?
What PCB design software do you use?
I use Eagle for a variety of reasons. It is a limited version of Eagle on the free license, but there are a couple of excellent free tools. I hear KiCad is incredibly popular. I have actually been meaning to have. Oh yeah, okay. I have actually been meaning to look. My intention is to move over to KiCad sometime in the near future, but when you do these, they have the standard parts libraries, but you also tend to end up making custom parts. And my custom parts library is a little bit too big for the thought of having to remake it to be. But no, I've heard a lot of very good things about KiCad, and I'm sort of in the middle of moving over. Yes. Anyone else? Yes?
You transmission lines, Dan, which I thought was an interesting thing. Have you actually built any PCBs with transmission lines?
I have to an extent. The problem is with a lot of the cheap board houses is they don't control the permittivity of the FR4.
And that was the point I was going to make. Yes. Okay.
Yeah, so they're fine at low frequency. They're fine at low frequencies, you know, HF stuff. Am I okay? They're fine at low frequency stuff. Obviously, if you're going up to gigahertz, it's not the way to go. But it comes back to that, you get what you pay for. And a lot of time, it doesn't actually, you know, if you make your RF deck on proper stuff with a proper manufacturer, that's okay. But for just the control circuit or a couple of relay switching, you know, they're perfectly fine for that sort of thing.
Okay, thank you.
Any more for any more?
Okay, just like to say many thanks to Dan for a phenomenal presentation, an insight into design research, innovation in amateur radio, very much alive and well. And if you've not already tried your hand at building some of this this technology, then it's certainly recommended with the new chips and components that are available to us today. So many thanks, Dan, and much appreciated.